So we learned about the dot product, which is sometimes called the scalar product or inner product between two vectors, and that helps you determine things like the angle between them. Cross product can also be used to help find the angle between them. Really, it's the magnitude of the cross product that will help. More commonly, it's used to help you find the normal to a plane, because really it finds the normal between two vectors. And so if you have two different direction vectors and you find the normal, that basically you can get the Cartesian equation of a plane. Just need that point to get the constant term. So two major ones. As well, with the magnitude of the cross product, you can extend that into calculating area of a triangle easily formed by those two vectors, or a parallelogram. So we'll do those as well. Okay, so cross product. So an actual cross has to be shown. Two non-collinear, non-zero vectors. Here's the definition. Notice this is the magnitude. So this is a number, what you get out of here. Okay, this is a number. This is very similar to the dot product, except it's signed now. So we know that that's a number. Magnitude is a number. Okay, theta is the angle between the two vectors. And really, we can delete this. Most times, it really actually depends on which direction your vectors are going. But it's the angle between any two vectors is either less than 90 or, so it's acute or obtuse. So you can just leave that part out. How do you get the actual cross product? Using the components. So this might look kind of crazy, right? Really what it is, if you continue on taking math courses at university, you'll learn a lot of properties about matrices. One of them being the determinant. You don't have to know what that means in this case, but the process of taking the determinant of a 3x3 matrix is basically laid out here. For a 2x2 matrix, so let's say we had just any matrix here. Determinant of A, B, C, D. If you have a 2x2 matrix and you're finding the determinant, that's going to be equal to AD minus BC. So the diagonals there. Okay? And it really helps you determine if you have, what are the reasons for using a determinant is it can help you determine whether a system is consistent, so whether you have going to have a point of intersection or not, if these were the coefficients of x, y, in a system, but we don't get into that. The process of taking the determinant is multiplying the diagonals and subtracting them. When you get to a 3x3, then the process, really what it is, and take a look here, notice how, oh, I just did, this is it, just in general, this is not for vectors, this is how to just take the determinant, yeah. But now in here, with vectors, because we're dealing with vectors, 3 components, so there's one of the vectors A, there's the other vector, those are the components. They're now shown horizontally in this matrix. And the first row are the standard basis vectors. So in terms of determinant of a 3x3 matrix, you basically take the first component, okay, and that here is vector I, kind of cross that off, and take the determinant of the remaining square matrix. So A2 times B3 minus A3 times B2, or switch it around. Okay. Then the next one
is where we cross off the first row and the second column. Notice how now it's the opposite sign here. So now we did take the determinant of the remaining square matrix, 2 by 2. So A1B3 minus B1A3, but with the opposite sign. And then the last column is there. Okay, so that A1B2 minus B1A2. Now, when we show this, if you take a look in your formula booklet, it actually doesn't show this process. It goes right to what we end up with here, these three components, because that's for I, J, and K. So really what that's equal to, and this is more often what you'll show it as, your vector. Okay, when you take the cross product of two vectors, you get a vector. And then there's your first component. Actually, I got to write a little bit smaller. A2B3 minus A3B2. I'm just going to put the A's first. And then the next one will be opposite to A1B3 minus A3B1. And then the last one, A1B2 minus A2B1. Okay. That's what you'll see in your formula booklet.
Pretty sure they don't show it. So cross product is the same as vector product. We'll call it vector product there.
Okay, so when I set up something like this to do, I show my, in this case, this would be A1A2, A3, cross product B1, B2, B3. Okay, how do I get that? Well, that's what I do is I cross off the first entry and I take the determinant of the remaining square. So A2B3 minus A3B2. Okay, then I move back down here, cross off the next. A1B3 minus A3B1, opposite sign. Then I move this down here, A1B2 minus A2B1. Okay, so I don't show it in that matrix form. Certainly don't show this. That takes a lot of time, right? Because really you're wanting to likely show it as a column vector like that. Okay, so no, you don't have to memorize it. It's in your data booklet, but not a bad idea. All right, so let's practice some. The first one, so there's a vector A and vector B. It says determine the magnitude of A cross B. Two methods. First one, find the angle between the two vectors, and then use this definition. Helen? Yep. Well, that's the definition of a determinant. So we'll show you, wait till the next example on the next page, and we'll do it the long way, and then you can kind of see why it changes. But that's just the definition of a determinant of a 3 by 3 is that the middle component is the opposite sign. So we're not going to get into the meanings behind that. But we'll see. 4 by 4, I forget what the formula is. It's much more complicated. But again, you would be splitting it into 3 by 3s, and then from a 3 by 3 down to a 2 by 2. Okay, so find the angle, so using this definition, so the angle between two vectors that we know from before is the dot product. All right, so in this case, cosine of theta is the dot product, so 2, 1, negative 1.
Okay, gonna keep it exact. So don't use your calculator, get the cosine ratio and use that to get the sine ratio. And I wouldn't rationalize it, right? We're not at the end of the question yet. From there, so for this definition, we know magnitude of A is 6, magnitude of B is 14, and then we want sine of theta. Well, here we have cosine of theta, so that's 7 over root 84. So then we can solve for the missing side. Pythagorean theorem, 84 minus 49 is 35 square rooted. Simplify that. Which is just, that's how we got root 84. Okay, and then method 2 is to actually calculate the cross product of those two vectors using components. Okay, so you do that. Then take the magnitude of the vector that you get. See if it's the same.
Okay, so you can start with your one like that. So -3 minus -2 is like adding 2, so that's going to be -1. Then opposite of -6 minus -1, so that's going to be opposite of -5. And then 4 minus 1 is 3. So really that's -1, 5, 3. Therefore the magnitude so it's going to be 25 plus 10 is 30. Same value. So turn to the next question. Area of a parallelogram defined by those vectors. So that means those are two sides of the parallelogram. Okay, and if it's a parallelogram, there'll be parallel sides to those vectors. Okay, so think of the formula for area of a parallelogram is base times vertical height. So you don't have that. Those vectors are not perpendicular. It's a dot product. They don't give you 0, so you know they're not perpendicular. So think about how between those two vectors you can find the perpendicular height of that parallelogram. Just using trig. Okay, so parallelogram looks something like that. Right, so area would be base times height divided by 2. In this case, our base is magnitude of A. Our height, we're not sure what that is, right? Call that angle theta in there. Then sine of theta is h over the magnitude of b, because that's the hypotenuse. Okay. And so h equals magnitude of b sine theta. And then in terms of the area calculation, so the base of the parallelogram in this case is magnitude of A. The height is magnitude of B sine theta. Oh, sorry, I put over 2. That's for a triangle. This is base times height. So there, that is the magnitude of the cross product. So the area of a parallelogram formed by two vectors is equal to the magnitude of the cross product of the two vectors. So rather than calculate the angle between them, right? Why go through all that? That's equal to, I'll put it underneath, the magnitude of A plus B So, A times B. So 4 minus 6 is negative 2. And then opposite of negative 4 minus 0. And then negative 3 minus 0. Okay, so now this one.
Okay, next example, determine a vector normal to both. So do like we did back last week, right? So think about the dot product. If it's a normal vector, that vector dot product with A should give you 0, and the same normal dot product with B should give you 0 if it's perpendicular to both. So set up a system. So we're kind of doing it the long way to see if we can see a relationship between a cross product. So use the dot product in example 3A. And then you'll have a system that you can actually use your calculator to help you solve. You don't want to do it algebraically.
So you could call the normal vector, you can call it A, B, C to make it, no, actually we've used vectors A and B there, no. Let's just use N1, N2, N3. Okay, so the normal with A is equal 0. then solve that system. It's 2 equations in 3 unknowns. You can do it algebraically or use your calculator like we learned. Okay, so matrix, this is the 2 by, so we're going to edit. I've got a 2 by 4, so 2, 1, negative 1, 0, and then 1, 2, negative 3, 0. Okay, then matrix math, RREF of that first A for mine. You can go to math frac. One, zero, 1, third, 0, 0, 1, negative 5, thirds, 0. So, that is, in this case, n2 minus 5 thirds n3 equals 0. So I'm going to let n3 equal some parameter. You could actually let it be a number, but I'll let it be a parameter multiple of 3. So let's say 3t. Then n2, bring that over to positive, that's going to be 5t. And then n1, bring that over as negative t. So our normal vector is t times negative 1, 5, 3. Okay, so we really don't care about the t in normal vector. It can be any multiple. This is telling us the direction. Okay. Now in the second part, find the cross product, doing in component form. See how that compares to this. Okay, so cross that off. Negative 3 minus negative 2 is negative 1. 2 times negative 3 is negative 6 minus negative 1. Change the sign, so negative of negative 5, right? And then here, 4 minus 1 is 3. So that ends up being negative 1, 5, 3. This is the same. So what do you notice? They are the same. So, therefore, the normal vector to A and
So kind of a summary there on the next page. A little bit different notation you can see in the box there. Notice how there's an N, a little kappa.
Okay. So notice how there's no magnitude symbols, but this is the magnitude of cross product. There's a vector there. So that's what makes, if you have the magnitude of the cross product, then you can't, it's not equal to the cross product of the two vectors. This is a vector, okay, and this is a scalar, a number. But this is a vector, right? So this is a vector and that's a vector. So that's how those can be equal to each other. So theta is the angle between the two vectors. And again, you can just summarize with between 0 and 180. And the little kappa is the unit vector perpendicular to both A and B. So that gives you the direction, right? So that's how this vector can be the same as this, because this has the same direction as that vector. Its size is only 1, right? It's a unit vector. This determines the size of it, okay? I'm not going to use that too much, but just be aware of that, okay? And then, of course, this is the actual magnitude of the cross product. There's the geometric definition. The actual cross product can be shown like that, or as I said before, it's A2B3 minus A3B2, A1B3 minus A3B1, A1B2 minus A2B1. And that's how it's shown in your data.
Okay, so the direction of that unit vector, N. So in the next example, it says determine the cross product of I and J and I. Right? They're the same vectors. Order kind of matters. Not significantly, but that's what we're going to see in this case. What the difference of the order of the vectors when you take the cross product. So vector I is 1, 0, 0. Vector J is 0, 1, 0. Take the cross product. What do you get? Think about what you should get. Because along the x-axis and along the y-axis, the cross product should be perpendicular to that, which would be the z-axis. Okay?
So determinant method really means what we've been doing. You don't have to show the whole matrix. Let's start and go down. Logically, you think it should be something going along the z-axis. So 0 minus 0 is 0. Move this down. 0 minus 0, opposite sign of 0 is just 0. Back down. And then 1 minus 0 is 1. Okay. Which is really equal to k. And then j plus I. in any case. When you cross that off, you get negative 1. Okay. So if you look back to the chart or the summary general table, it says determine these using the method involving sine theta. So that was saying, okay, I cross J equals the magnitude magnitude of I and J is 1, so 1 times 1. And the angle between them, that sine, is 90 degrees between vectors I and J. Sine of 90 is 1, so really we get that unit vector, right? But that still doesn't tell us a direction. So that's the issue in using this particular method here. You have to know the direction of it. And then J, you do it the other way around, still meets at 90 degrees, so you'll still end up, so same. Okay, but we know that those are actual opposite to each other, so that, again, that unit vector, normal unit vector, is kind of the problem when you're using it that way. Okay, so really, we don't know what that unit vector is. How do we deal with this? Well, really, you're going to use the component form, not this, unless you know that direction. Now, we can look at we'll look down below in terms of what direction each of these are going to go in. But here, use the so use the determinant definition of cross product so that you do know the direction of it. And then the next part, if you've taken physics, you've probably, I think you use something similar in terms of direction of, is it current? Yeah. So kind of the same process to know the direction of your normal. So right-hand rule is used. So if the vectors A and B are in a completely horizontal plane, so 2 on a plane, which really they can always be moved to that and still have the same direction. Yeah, so if you move them up, so still horizontal, what's the direction of the normal? So basically you start whatever's listed first. So if A is listed first, you take your finger and you curve around to B, and your thumb tells you what's happening. So here, this is on the paper basically. So if I curve around, it's going up. If I then do the other way, going from B to A, then I'm having to go this way and curve around, and so my thumb is going the other direction. So kind of like pointing at the first vector to start. Okay, so that's your first. So your thumb there is going upwards. If I have to start B, then I'm having to go the other way around. So it's either out of, if you're looking at 2 vectors on a piece of paper. So I think there's some examples down here. Here. So if we're doing U and V, I'm doing the cross product, then in order to start with my index finger going from U, then curving around to B, my thumb has to be going into the paper. Here, if I start here and curve around to V, my thumb has to go out of the paper. Here, to start U, go to V, my thumb has to be into the paper. So it's on a piece of paper, and U is to the right of V, then the normal's coming out, right? If U is on the left, then it's going in. But they're just directly opposite, okay? The components will be the same, except opposite signs. So this is going to be going, U going in, U going out, U in, and then
Does that really matter a whole lot? When you're finding normal vector, really we're going to be using this to find equations of planes. If you switch the order of the two vectors on your plane, like one person might do A cross B to get the normal, another might do B cross A. But remember, a Cartesian equation, you can simplify that. So your signs of your X, Y, and Z are the opposite of someone else. Doesn't really matter. You're going to reduce it so the X coefficient is positive anyway. What will end up happening, though, it'll be consistent with the constant term. So really doesn't matter a whole lot, but just be aware that the order does change the sign of that normal vector, the order that you do the cross product. So that's where we are stopping, I think, for today.
yeah. It's actually 2 example 5s.
We're starting at the end of this page. So we're starting this, and then tomorrow is the last day of vectors. Wednesday is a practice day, catch-up day, and next Monday is a catch-up day. So you do have some time to catch up.